In this lecture, we're going to look at the right triangle trigonometry definitions. Let's start with an application from geometry. Here we're asked to find the height of this tower using the measurements in this diagram. The important thing to notice is that there are two right triangles in this diagram. The smaller one that has a vertical leg of 6 feet and a horizontal leg of 8 feet, and the larger one that has the vertical leg of h and the horizontal leg of 40 feet. The smaller triangle placed inside the larger triangle indicates that they have the same base angle. So this angle here in the smaller triangle is equal or congruent to the base angle here in the larger triangle. You can imagine that a 6-foot pole is placed vertically so that the top of the pole is in the line of sight from this point on the ground to the top of the tower, and then these two horizontal distances could be measured from that point. Since we form two right triangles with the same base angle, that means that the ratio of this vertical leg to the horizontal leg in the smaller triangle, which we can measure, has to equal the ratio of the vertical leg to the horizontal leg in the larger triangle, and we can use that to solve for h. This is an application of similar triangles from geometry. Similar triangles have the same shape. They're basically scaled copies of each other. So similar triangles will have the same angles, and they will have proportional sides. Either of these conditions is enough to guarantee that two triangles are similar. So if we have two triangles with the same angles, then we know that they will have proportional sides. And if we have two triangles with proportional sides, we know they'll have the same angles. We know these two triangles have the same angles because we can see in the diagram they both have a right angle and they both have the same base angle. And since the angles in a triangle add up to 180 degrees, subtracting these two angles from 180 will give us the same third angle in both triangles. So these are similar triangles and they will have proportional sides. That means that the ratio of 6 to 8 in the smaller triangle has to equal the ratio of h to 40 in the larger triangle. This is a proportion, and now we're going to solve for h. We just need to multiply both sides by 40 to cancel this denominator. That leaves us with h equals 6/8 times 40. This simplifies to 30, and our units are feet, so the height of the tower is 30 feet. The important thing in this example is that the two right triangles have the same base angle, and that guarantees that the ratio of the corresponding sides will be the same in both triangles. But really, this ratio is dependent on this angle. If we change the angle, then these two sides will change relative to each other, and the ratio will change. So in a right triangle, the ratio of any two of the three sides is a function of this angle. And that's the foundation of trigonometry. A trigonometric function pairs up each of the possible angles with the corresponding ratio formed by that angle in a right triangle. And that means if we know the measure of this angle, we can get this ratio from a trigonometric table or a calculator, and we can apply it here to solve for the height. We don't need to construct a similar triangle and measure the sides to come up with this ratio. So now we want to give the definitions for the trigonometric functions. There'll be one function for each of the possible ratios we can form with the three sides in a right triangle. We'll start with any acute angle theta. An acute angle is between 0 and 90 degrees, so we can form a right triangle. We're going to label each of the sides of this triangle with respect to this angle. So we'll start with the leg that's opposite to the angle. The other leg will be adjacent to the angle. And of course, the hypotenuse is always opposite the right angle. There will be 6 possible ratios that we can form out of any two of these three sides of the triangle. And so we're going to define 6 different trigonometric functions, one for each of those ratios. We'll start with the sine function. Sine is abbreviated sin. Sine of an angle is the leg opposite to the angle over the hypotenuse. Next we have cosine, which is abbreviated cos. Cosine of an angle is the leg adjacent to the angle over the hypotenuse. And then we have tangent, abbreviated tan. Tangent of an angle is the leg opposite the angle over the leg adjacent to the angle. These first 3 functions can be considered the primary trigonometric functions. These are the 3 you'll find on your calculator, and these are the three you'll find in most trigonometric tables. Any two of the three sides of this triangle can be found in one of these three ratios. So if you're using a known side length to solve for an unknown side length, one of these three ratios will work. A common way that people remember these definitions is SOH CAH TOA. SOH stands for sine is opposite over hypotenuse. CAH is cosine is adjacent over hypotenuse. And TOA is tangent is opposite over adjacent. The remaining three trig functions are the reciprocals of these three. We won't really need those to help us solve right triangles, but we will use them later in this course, and you will see them in future math courses as well. So we'll go ahead and define those now. We'll start with the reciprocal of the sine function. This is called the cosecant, abbreviated CSC. This is the hypotenuse over the opposite leg, the reciprocal of sine. The reciprocal of cosine is the secant function. Secant is abbreviated SEC, and that's defined to be the hypotenuse over the adjacent leg, the reciprocal of cosine. And the reciprocal of tangent is the cotangent function. That's abbreviated COT, and that's defined to be the adjacent leg over the opposite leg, the reciprocal of tangent. When you're learning these 6 definitions, I think it's easiest to start with the 3 primary functions, and SOH CAH TOA is a good way to remember those. And then remember which of the reciprocal functions pairs up with each of the 3 primary functions. Whenever we're displaying all 6 ratios at the same time, we will always write the reciprocals side by side so we can see them paired up, and it'll make them easier to remember. Once we introduce all this notation, things might start to seem a little bit abstract, and it's easy to forget the basic idea behind all of this. That basic idea is that this acute angle determines the specific shape of this right triangle. It determines how long each side is relative to the other sides, and that's measured by these ratios. Here's 3 different angles, and we get 3 different shaped triangles. Let's suppose in this middle example that the opposite leg is half the length of the hypotenuse. That would be a ratio of 1 to 2. It doesn't mean that the lengths have to be 1 and 2. It just means for any right triangle with this angle, the opposite leg will always be half of the hypotenuse. And that ratio is given by the sine function. So the angle determines the shape of the triangle and therefore determines the ratios. But we could also say that the ratios determine the shape of the triangle and therefore determine the angle. So the trigonometric functions just pair up the angles and the ratios. These pairs can be displayed in a table. For example, here's a table showing the sine ratios for some of the possible angles. And these trigonometric tables were very important before we had computers and calculators to compute these ratios for us. In this middle triangle, we had an angle with a sine ratio of 1 to 2, or 1/2. If we look in this table, we see a sine ratio of 0.5, which is the decimal equivalent of 1/2, and we can see the corresponding angle is 30 degrees. So we know in this triangle, this angle will have to be 30 degrees. We'll look at these tables in more detail in some upcoming lectures, once we've had some more practice applying these basic definitions.